In this demonstration, I'll look at a modal analysis followed by a transient dynamic analysis of a flat plate, which is 400 millimeters long by 100 millimeters wide and 25 millimeters thick. It is fully fixed at x equals 0 edge, and it's made of steel, and we are going to look at finding its first few natural frequencies and their mode shapes. And this demonstration is based on the ANSYS verification manual example 66, so it's similar to that test case, and that can be found on ANSYS users manual. And also Timoshenko and Young also looks at the theory of this particular problem. Following the modal analysis, we'll look at a transient dynamic response of this plate, and we'll apply a force on the right edge, and we'll apply it so that it goes up 20,000 newtons in 10 milliseconds and goes down again to 0 in 10 milliseconds, and it's a ramped load, almost like an impulse loading on the right, and we'll look at how that will affect the response of the plate. Okay, we'll start with our project schematic on Workbench again. So we'll bring our modal analysis tool, and we'll start by creating our geometry in Design Modeler. In Design Modeler, we'll choose XY plane and simply create a sketch of a rectangle there, and that will be dimensioned so that it is simply 400 millimeters long and 100 millimeters wide. So we can go to dimensions and create our horizontal dimension. So because I'm in the meters mode, I need to change my units on the fly, so that's 0.4 meters, and let's zoom in. And in terms of the height, the vertical dimension is 0.1 meters, so that is 0.1 meters. So we can zoom in there. So that's all I need in terms of my sketch. Then we'll go back to my model and select my sketch, and then create a concept of a surface from the sketch and generate that. So that creates one part, one body. Thickness doesn't need to be entered in this case. We can enter that within mechanical. So we'll next run mechanical. We can see that the mechanical starts and the design modeler geometry is attached. So the surface body will need a thickness defined, so that's 0.025 meters. That's 25 millimeters. The material is steel by default again, and we just need to create a mesh. So sizing on that surface, we can make that an element size of 0.05, let's say, for 50 millimeters. And what will that give us? So that's a few elements really created on that surface area. So these are effectively shell elements. Now the next part is to apply our boundary conditions, and we can select the edge on this corner by using our edge filter, and then apply a fixed boundary condition there. So that means it's going to fix displacements x, y, z, as well as the rotations in x, y, and z axis. And the other boundary condition will be the force when we apply the transient analysis, but this is a modal analysis, and we are interested in finding mode shapes. We don't need to apply any forces in this case. So the next bit is to apply our results, which is total deformation. Let's say first 5 modes. So total deformation for mode 1, that is for mode 2, mode 3, mode 4, and mode 5. So next we can solve this problem. And we can see that our mode shapes are starting from about 128 Hertz, going to 489 Hertz, 797 Hertz, etc. Almost up to 2.5 kilohertz range. So these are fairly high. It is a relatively stiff structure. So if you look at mode shape 1, total deformation 1, that is a simple up and down motion. Total deformation 2 is sideways. Total deformation 3 is a bit more complex shape. Total deformation 4 is a torsional vibration mode. Total deformation 5 is another higher order vibration mode. So looking at these, we can see that the first mode is 128 Hertz, and if the loading that we are going to apply for our transient analysis is going to particularly excite this simple up and down motion, we can then say, okay, let's do our transient analysis based on this first mode of frequency. So we can calculate our integration time step as 1 over 128 times 20. So that will be necessary for our next part, which is the transient dynamic analysis of this flat plate. And now we will add the transient dynamic analysis to our project schematic. So from the analysis systems, we can drag the transient structural and drop it into our project schematic. If I drop it under solution, that will create a transient dynamic analysis based on a mode superposition using the mode shapes defined in the first analysis. However, if I drop it onto the model, that is just going to share everything up to model and not the solutions of the model analysis, and then that will define a full transient analysis. So we can continue editing our model, and we can see that the model A5 cell is shown here, and transient is added as B5. We need to look at initial conditions, so you can see that the model isn't included here, and we need to look at our analysis settings, and we can define, say, number of steps. We'll start with one step and step end time of 1 second. We can turn on automatic time stepping and use sub steps. So let's say define 1000 sub steps. So that will mean each sub step will be 1 milliseconds. So if we had one load step and we divided that to 1000 sub steps, each sub step will define 1 millisecond. Now we've calculated our mode shape. The first mode shape was at 128 Hertz. So that can help us calculate the integration time step. So that will be, let's calculate using the calculator. So the first mode was 128 times 20. 2560. So our integration time step has to be 1 over that. So that's 0.4 milliseconds. So that's a pretty small number. So the initial sub-steps we have entered there isn't really sufficient to analyze this problem. So we'll need to look at really something like 3000 sub-steps in 1 second. That's a fairly long solution time. We can try to do this solution and see how long it takes, and we can try to adjust what happens. So in our transient analysis, this is our analysis setting. We defined 1 steps and 1 second at the end of the step and 3000 sub-steps, and time integration is on. And damping controls has to be checked here. Numerical damping, we can make that manual, and then numerical damping value is 0, just so that it is a completely undamped structure. Stiffness coefficient and mass coefficient, the alpha d, beta d, etc., those coefficients are 0. And in the solution we'll enter the solution quantities, but first of all the boundary conditions need to be re-entered. So the edge needs to be fixed, so that edge we need to fix it fully, and on that edge we need to apply a force. So that force was going up, and we can define it in terms of its components, which is in the z direction we want it to go up to 20,000 newtons, but in this case it's going up to 20,000 newtons as a step change. So this is a plot of how this is going to work, but what we said was this force needs to go up to 20,000 newtons in 10 milliseconds. So 0.01, at 0.01 it needs to reach 20,000, and then it needs to come back so it needs to come back to 0 at 0.02, which is 20 milliseconds, and it can continue vibrating beyond that, and to start with it is 0. So it's going from 0 to 20,000 newtons and coming back down again. And let's see how this load will run. And in solution we need to fix some solution parameters like the deformation and the stress. The equivalent stress will be interesting, and also the normal stress, and the one that's in the x direction will tell us the bending stresses in particular. So we can now solve this problem, and maybe we can adjust the parameters. Okay, the solution is done, and we can see that there's an initial spike in the displacements, and then it settles into some sort of continuous vibration. We can animate this. I think the first few seconds will be, or first few milliseconds will be more interesting. So we can select that. We can increase the animation duration to 10 seconds with 100 frames, just to be able to capture more precisely. So let's see how that will look. So this is the plate being sort of pushed up, and because of the inertia it sort of continues to go up, and then it continues to vibrate beyond that point. So I think the most interesting behavior of this plate can be observed in a few milliseconds really. So this point is about 0.1 seconds. So we can change how this analysis was run. We can look at our analysis settings. We can enter our solution. For example, this time we can change it to step end time of say 0.05, which is 50 milliseconds, and we don't want to create 3000 steps between 0 and 0.05, so we can change our solution. Instead of sub steps, we can use time, and our time in this case is now adjusted to about 1.6 e minus 5 seconds. So that is taking into account 3000 steps, so I don't want to use that. But if you remember that our integration time step was about 0.0004 seconds, we can use that here. We can copy that and then paste in here and in here as well. So I'm using the same as the initial time step, minimum and maximum values. So that will create a number of steps during this solution. So our force is again going from 0 to 20,000 newtons and then coming back down. So this is 10 milliseconds and another 10 milliseconds to get the force down, and 50 milliseconds when the simulation will end. And we can solve this problem again, and it should run much faster. So this time it only took about 14 seconds rather than 5 minutes for the solution. So we can see a better defined response of the structure. We don't want to see the minimum or the average, but just the maximums of the displacements, for example. So the maximum displacement, if we can change it to maybe units of millimeters, it's probably easier to visualize. Millimeters, kilograms, newtons for the units. So in terms of the displacement, it's going up to 17 millimeters. So we can animate that. So we can do that within a 3-second animation. So when the load is applied, it's going up and it continues to go up because of the inertia of the system, and then it settles into some sort of free vibration mode. In terms of the equivalent stresses, we can see that the maximum is reaching 791 megapascals. So that's a fairly high vibration related stress. And normal stress, just due to bending, we can run that as well. So we can see how that bending is created at the bottom, and especially the maximum is reached within a few milliseconds just after the maximum load is applied. And we can look at a simple static analysis of this structure to find out what is the effect of the dynamic loading. Going back to our project schematic, we can create a static structural model, just sharing the original finite element model and geometry and engineering data, and we can continue editing our mechanical model, and you'll see that at the bottom a static structural analysis is added, and all we need to do on this one is define the boundary condition, which is fixed at this edge fully. So under context, create a fixed boundary condition, and at the other edge fix a force, apply a force, and the value will be similar to the transient analysis, but in the z direction it's a static load of 20,000 newtons. So this is a static analysis, and we're just applying that load, and in the solution we want to see total deformation and equivalent stress, von Mises, and then bending stress, normal direction. So we can solve that. And we can see that maximum total deformation is about 16 millimeters, which is the static solution, and equivalent stress is about 721 megapascals at the base of this structure, and normal stress is about 811 megapascals. So the dynamic effect would be that the total deformation is higher when it's dynamics included, and equivalent stress is also higher, almost like 70 megapascals higher in the transient analysis compared to the static analysis.